This is lesson 3 from Unit 1. So Unit 1 is on sequences, and today we're going to be talking about growing dots, which is pretty similar to the one we just covered, which was growing dots. But now we have growing dots. And let's move this over just a little bit so we get the whole slide. There we go. So today's objective is I can accurately describe a growing pattern by drawing a table, drawing a graph, or writing an equation in 1 out of 2 problems. This might sound really familiar because this is the exact same objective we had yesterday. But we are going to look at slightly different patterns today. So here's some things to think about. How can I label a picture to show how I see a pattern? And how can I use math to represent a pattern? All right. So let's start with exponents. Let's do a quick review of exponents. And I need a pen. Let's find a good color today. Maybe this green. And 3 to the 5th power. So you see 3 is what we call our base, and 5 is what's called the exponent. And how we interpret that is our base is going to be multiplied by itself. And then we're going to do that the number of times in the exponent. So this is 3 times 3, and we do that 5 times. So we go 1, 2, 3, 4, 5. 3 times 3 times 3 times 3 times 3. Now we could do that all by hand, but I highly recommend it in a calculator. You might have, oops, let's zoom back out. You might have a symbol on your calculator that looks like that. That's going to be your exponent. And you would just do something like 3 caret, that's what we call that, caret 5. So 3 to the 5th. So if you type that into your calculator, see what you get. I get 243. We can write the expanded forms down here. So we see these exponents, and we know that this is 6 multiplied 3 times. So we would call this 6. Oops, we need an actual pen. This would be 6 times 6 times 6. 4 squared would be 4 2 times 4 times 4. 8 to the 6th is going to be 8 multiplied by itself 6 times. So here we go. 1, 2, 3, 4, 5, 6. That's how we would write the expanded form. Over here, we'll write the exponential form, so we're going to go the other direction. This is 2 multiplied 4 times, so that's going to be 2 to the 4th. This is 5 multiplied 6 times, 1, 2, 3, 4, 5, 6, so 5 to the 6th. And then we have 7 3 times. What do you think that's going to be? That's going to be 7 to the 3rd. You can see why we might want to condense the notation like this, because writing this out a lot of times, like if it were 10, 5 to the 10th, or 5 to the 100th, that would take a really long time to write. So we have this condensed form that makes it a lot easier to write. All right, so let's get into our patterns, because that is what we are all about this unit, patterns. What seems to be happening each minute? Let's see. So we're looking at dots again, dots at different minutes. But these are different dots than the ones we looked at in the last lesson. At the beginning, we start with 3 dots. At 1 minute, we have, let's see, 1, 2, 3, 4, 5, 6. And then at 2 minutes, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So how are the dots changing? What do you think? Maybe they're going up by 3 each time. Maybe they're going up by 4. I don't know. Let's see. Let's look at a few more and see what's happening now. Oh, at 4 minutes, there's a ton of dots. It must be going up by more than 3. Maybe they're doubling. We have 2 and then 4 in this group. 8 in this group. 2, 4, 6, 8. And then, let's see, this is a 4 by 4 square, so that's going to be 16. Yeah, it looks like maybe they're doubling. Interesting. So let's draw or describe our patterns. We described it just now. Let's see if we can draw it. And I might recommend using colors. It can be really handy to use colors. So watch this. We'll circle the same group in the same color so we can watch it over time. So there's one group. Maybe I'll choose pink for the next group. Here's pink. And if you're really into colored pens like I am, you can use your colored pens and be super happy about it. And then maybe we have this blue color. So now you can see really easily, if we're looking at the blue group, it goes 1 to 2 to 4 to 8 to 16. And all of these groups are symmetrical, right? They all look the same at every step. So we could just multiply, we could count 1 and multiply by 3 to get the total one. So for instance, here we have 16, and we'd know that this is 16 and this is 16. So we'd know the total dots are 16 times 3, which is 48. Can we see a pattern with a table? So we did talk about a few different ways to model a pattern yesterday. A table was one of them. So let's fill in the table with the number of dots. Let me grab a different color here. At 0 minutes, we had 3 dots. There's 1, 2, 3. At 1 minute, there were 6 dots. 1, 2, 3, 4, 5, 6. At 2 minutes, there were 4, 6, 8, 10, 12. 12. Okay, so that's filled in for us already. At 3 minutes, how many dots are there? Well, we have a few different methods. Remember, we just did grouping. We see that there are 3 symmetrical groups. Each one has 2, 4, 6, 8. So we could take 8 times 3 and see that that equals 24. So that's one of the ways we could do it. But another way we could do it is we can notice a pattern in the table. Let's see. So we started with 3 and we went to 6. Then we have 6 to 12. And that looks like it's doubling, right? We're multiplying by 2 on each step. And that's the same as what we noticed with the dots. Those are the words we said, right? It's doubling each time. The 4 turned into 8. It got twice as big. So if we do this pattern, if we continue on with this pattern and multiply by 2 again, 12 times 2 is 24. Notice that's the same as the number we got over here. 8 times 3 is also 24. So counting the number at 4 minutes would be really annoying. There are a lot there. But if we just multiply by 2, how many would you expect that to be? That's 48. We have 48 dots at 4 minutes. All right, so how many dots would there be at 5 minutes? We don't have a picture this time, but we could probably guess it'll follow the same pattern. We're going to multiply by 2 again, and we see 96 dots. So now let's compare today's dots to the previous lesson's dots. So this was the one we looked at in the previous lesson, and this is the one we're looking at today. This one looks like it's growing pretty fast, right? We've got a lot of dots coming at us really fast. So the previous pattern we saw was we added 4 each time. We had 1, then 5, then 9. We were adding 4. Remember, they went around in that X position, that X formation. So plus 4, plus 4, plus 4 each time. And this is called an arithmetic sequence. We're actually going to do vocabulary in math. What? Since when do we have words we have to learn in math? Yes. This is called an arithmetic sequence, like arithmetic. We're adding. We could also be subtracting or subtracting. We kind of group those together as similar operations, adding or subtracting at each step. Now, if we look at the one we did today, we are multiplying by 2 each time. And this is called a geometric sequence. So arithmetic sequences add each time. Geometric sequences multiply each time. And similar, like we did before, like this was or subtract. We can add or subtract. What's the paired operation we pair with multiply? We could also be dividing at each step. That would also be called a geometric sequence. So arithmetic is when we're adding or subtracting. Geometric is when we're multiplying or dividing. So how do their graphs compare? We compared their tables. We saw that they were adding each step or multiplying each step. Let's see how the graphs compare. So this is the graph we did in the previous lesson. This is our arithmetic sequence. We determined it was a straight line that was pretty steep, had a slope of 4, which was the same as our change. Let's graph today's graph and see what it looks like. So remember, we have our x and our y, and we remember that y to the sky, and x is the other one. And let's graph. So x is 0, y is 3, x is 1, y is 6, that's going to be here. 212 is up here. 324, oh, that's way off the graph already. It's way up at the top, even beyond where we can write. And what do you think? Can we draw a straight line through these? Do you think that'll work? We can try it. But it looks like these dots are actually getting way off that straight line. The other one's going to be way over here. So maybe a straight line isn't going to work for us. Maybe we need to do something more like a curve. Kind of goes up this way. We'll skip that slide, and we'll just ask if we put them on the same graph, this is what they look like. And we ask which one is going up faster. Can you tell? Well, it looks like this one's getting steeper and steeper and steeper, while this one's staying the same steep the whole time. So the blue one is going up faster, or the geometric sequence. That one is definitely growing faster. And does that make sense looking at the dots? Which one is growing faster in the diagram? Which one can you say is getting more dots in the picture? Or growing faster? So this one is definitely growing faster. That's how we described it earlier. It's growing much faster than this one. This one's growing pretty slowly. So geometric sequences grow faster than arithmetic sequences. Okay, so extra challenge. Can we come up with an equation to model today's dot pattern? Interesting. These ones are a little bit trickier, and so I don't expect you to be able to come up with this on your own quite yet. But we're going to look and see if we can figure out how to make an equation out of this. Now, we did look at exponents earlier in this lesson, so maybe we should use exponents. So let's think. Maybe let's start with y equals x squared. Let's see if those exponents will get us where we're going. So we have x and y, and so I'm going to start with 0, 1, 2, 3, 4, 5, and see if I can get them to match. So y equals x squared. I'm going to do y equals the number in the table, so I'm going to do that over here. This is going to be 0 squared, which is 0. Now that doesn't equal 3, so we already have a problem. So let's go back and try something else. 0 plus 3 is going to get us to 3, so we could do 0 squared plus 3 equals 3. So that'll get us the first one. Let's see if it stays for the second one. We do 1 squared plus 3. Now remember, I'm just plugging this 1 in for x. 1 squared plus 3 equals 1 plus 3 equals 4. Oh, but that's supposed to be 6. So that didn't work either. All right. So let's go back. And maybe even let's try something totally different. Instead of doing x squared, maybe let's swap those. Let's see what it's like if we do 2 to the x. What happens then? Well, 2 to the 0, we're just going to have a rule on that one. We've defined 2 to the 0 as 1 because 2 0 times itself doesn't make any sense. So that's just a definition. Any number to the 0 is 1. So we know this is going to be 2 to the 0 equals 1. And then we will have 2 to the 1 equals 2. And then 2 squared equals 2 times 2, which equals 4. Now these don't match, right? 1, 3, 2, 6, 4, 12. But notice, if I keep filling this in, 2 to the third is going to be 2 times 2 times 2, which is 8. We do get a doubling pattern here. This is multiplied by 2, this is multiplied by 2, this is multiplied by 2. So it looks like we're on the right path. We've got something right here. We've got the correct pattern. We basically just don't have the correct starting number. Interesting. Okay, so maybe we can delete these guys. Maybe let's try multiplying by 3 to get that first number. Then we would get 2 to the 0 times 3. We get 1 times 3 is 3. Then 2 to the 1 times 3, we'd get 2 times 3, which is 6. Oh, that matches so far. 2 squared times 3. We get 2 squared is 4 times 3, which is 12. It is doubling every time. How cool is that? Doubling, doubling. 2 to the third times 3. We put that in our calculator. We will get 8 times 3, which is 24. It is working. This is the pattern we were looking for. This is the equation. Y equals 2 to the x times 3. 2 to the fourth is going to be 16 times 3, which is 48. And our last one, 2 to the fifth times 3, is 32 times 3, which equals 96. Everything matched. Excellent. That's awesome. Okay, last extra bonus challenge question. How do we write this equation we just came up with in function notation? Do we remember function notation from the last lesson? Well, if you'll recall, we just replaced the y with this super fancy notation, which goes f of x. Now it's f of x because x is the variable that we're using up here. So f of x is our function of x equals 2 to the x times 3. So that is our equation in function notation. You can just ignore that slide, and today's objective is I can accurately describe a growing pattern by drawing a table, drawing a graph, or writing an equation. We did all of those things today in 1 out of 2 problems.